Hello everyone, and welcome back to another video. Today I have for you 10 integrals over here, of which 9 of them are indefinite ones, and then there's a definite one at the end. So please like, subscribe and share, and let's jump straight into this without any hesitation. So, what's our first integral? It is the integral of arc sine of x all squared. Just a reminder, I think 2 videos ago or something, there was a little bit of confusion. Arc sine just means inverse sine of x. So this integral, I could write it like this as well. It doesn't matter which way you write it. For me personally, the way I've written it looks nicer. So the obvious thing to do right now is to take a substitution. Let's say u is equal to arc sine of x, and then if we apply sine to both sides, you get sine of u equals x, and then do implicit differentiation for both sides. So cosine of u du equals to dx. And now if we rewrite this integral in terms of u, we get the integral of arc sine of x squared, which is u squared, and then multiplied by dx, which is cosine of u du. And clearly this is just integration by parts. For this I'm going to be using the di method. So d for differentiation, I for integration. I'll put some pluses and minuses on the side. So the idea is we have two functions here, u squared and we have cosine of u. Which one do we choose to differentiate and which one do we choose to integrate? Well, ideally we should choose u squared to differentiate, because if you differentiate it, it gets simpler as you go. So it goes from u squared, right here. When you differentiate it once, you get 2u. Differentiate twice, you get 2. Then you get 0. If you were to differentiate cosine, it wouldn't get simpler. It would just stay as cosine and sine and all that. So let's integrate cosine instead. If you integrate positive cosine, you get positive sine. Integrate positive sine, you get negative cosine. Integrate negative cosine, you get negative sine. So now, the idea of this setup is basically integration by parts, but in a table format. So if you were to multiply diagonals, you would get part of an answer of the answer, and if you were to multiply across a row at the end, you would get an integral. But since here we have a 0, there is no integral at the end, because integrate 0, you get 0. So therefore the answer to this integral in terms of u is equal to u squared sine of u. Make sure to not forget the pluses and the minuses in front of the table. So u squared sine of u plus 2u cosine of u. The reason why there's a plus is because the minuses cancel out, and then minus 2 sine of u. And we have one more thing left to do, and that is to return this integral from being in terms of u to being in terms of x. So given that sine of u equals to x, let's draw a quick sketch of a right angled triangle which satisfies that statement. So the sine is just the opposite over the hypotenuse, and if we have this type of triangle, the adjacent side would just be equal to 1 squared minus x squared with the square root all around it, and 1 squared is 1. So this helps us to know what cosine of u is. Anyway, back to the integral. So here we have u squared sine of u. Sine of u is just x, and u squared is arc sine of x squared. Arc sine squared of x. Alright. Plus 2u cosine of u. Well, cosine of u is just the adjacent divided by the hypotenuse, which is, according to our right angled triangle, clearly equal to root 1 minus x squared. And 2u, let's just put the 2 on the front, why not, like this. And then we have u, which is arc sine of x, like this. Finally, minus 2 sine of u, which is negative 2x. Finally, plus c, and that's our first integral. Thank you very much. There you go. I think I might highlight it. The only issue is because I'm on a dark background right now, it won't actually highlight it, it will just put a different colour on it, but that's good enough. Alright, the reason I've chosen a darker background is so that I could comfort your eyes for 40 minutes. Alright, next we have this awkward looking integral. The numerator is, well, it's clearly a difference of two squares. The numerator can be rewritten like this. Cosine squared x minus sine squared x when you expand everything out. So in other words, it's a difference of two squares. The denominator shall stay the same. 2 sine x cosine x and dx. Alright, now what do we have? The numerator, if you're very fluent with your trig IDs, this bit, cosine squared minus sine squared, actually is equal to cosine of 2x. That's our double angle formula. What do you notice about the denominator? That is sine of 2x. So if we rewrite this integral using those two trig identities, you get cosine of 2x divided by sine of 2x with a dx at the end. Now you may be asking, should we simplify cosine and sine to make a tangent? Well, it's pointless. We're doing integration, remember. We should keep it in this form so that we can take another u substitution. U is equal to sine of 2x. So if you differentiate both sides, you get du is equal to cosine of 2x dx, which is very elegant, I know. And then finally, we should divide both sides by 2 cosine of 2x to get our dx as du over 2 cosine of 2x. So this integral can be rewritten in terms of u as the integral of cosine of 2x over u multiplied by du over 2 cosine of 2x. And you notice that these cosines, they cancel each other out, which was the purpose of our substitution. So you're just integrating half of 1 over u, and you get half of ln u. I'll write it like this: ln, absolute value of u. Remember absolute value, because we're not looking at complex analysis, so we can't just put a bracket on there, we have to put a modulus. So finally, our last step is to replace u with whatever it corresponded to in terms of x. And u was equal to sine of 2x, as you can see from the top line on the screen. So overall, we have ln of sine 2x, of course, with the half up front, plus c. And that's our answer. Once again, another lovely answer. Let me just increase the thickness of the highlighter, that's better. Yeah, you notice that I'm on the OneNote app right now. What am I doing in the depths of these idiotic crevices, you may ask? Well, I'm just using it because it's easy to switch colours on OneNote compared to on the Apple Notes app. Right, now we have this weird integral with nested square roots. What is going on here? Well, the trick is to use power rules. So let's rewrite the integral as x to the power of 1. I'll put the powers in red. Times x to the power of a half. Whoops, there we are. And if you have two square roots within each other, it's like putting something to the half power twice, which is the same as putting something to the quarter power. So x to the power of 1 over 4 times x to the power of 1 over 8. I should keep consistency with the colours, shouldn't I? Dot 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 dx. And this integral can simply be rewritten as the integral of x to the power of 1 plus a half plus 1/8 dot dot dot. The reason is because of the power rules. If you have two terms with the same base, you can just add the exponents. And that's what we have. We need to just work out what this 1 plus a half plus an eighth is equal to. And it's actually equal to 2. So we have x to the power of 2 dx. How do we know it is this? Well, I'm going to use a concept called geometric series. So the idea is you have S, which represents the sum of the series of n represents the number of terms in that series, is equal to a, which is the first term of the series, multiplied by r, which is the common ratio of which each term is multiplied by or divided by, to the power of n minus 1 all over r minus 1. And in our case, n is just equal to, well, infinity, or you could, in order to not abuse the notation, you could apply limits. A is equal to 1 and r is equal to a half, because each term is being multiplied by a half to get to the next term. How do we know that this is true? How dare you assume this axiom? You may say to me, well, let us try and prove this so that we don't, I don't want to leave you hanging, you know what I mean? So Sn is equal to, how do we prove this? Well, firstly, what is Sn? Sn is just equal to a, which is the first term, plus ar, which is the second term. R is just the common ratio, plus ar squared, plus dot dot dot, plus ar to the n minus 2, plus ar to the n minus 1, right? Let me just move it a little bit across, like that. Perfect. The trick is, let us multiply all these terms by r. So, one sec. Let's do that like this. Multiply by r. So we have r multiplied by Sn is equal to, well, a becomes ar squared, ar becomes ar squared, plus dot dot dot, plus ar to the n minus 2, plus ar to the n minus 1, plus ar to the power of n, right? And let us treat these two lines as almost simultaneous equations. So let's find the difference between them. So that rsn minus Sn is equal to, well, this cancels out with that, this cancels out with that, all of these terms cancel out with those terms, ar to the n minus 2, all these cancel out, and you're left with this term minus this term. So you're left with ar to the power of n minus a. And now let's just do some basic factorization. If you factorize the left hand side, you get Sn multiplied by r minus 1. And if you factorize the right hand side, you get a multiplied by r to the n minus 1. And finally, all we need to do is isolate the Sn from the left hand side and bring r minus 1 to the right hand side like this. So there you go, there's a proof for this. This might be useful for those of you who are doing your A-levels. I don't know. Now back to this. In our case, a is equal to a half, n just goes to infinity. Sorry, a is 1, n goes to infinity, and r is a half. So in our case, s infinity is equal to the limit as n approaches infinity of a, our first term, which is 1, multiplied by r to the power of n, which is a half, all to the power of n, minus 1, all over a half minus 1. And clearly, if you apply the limit to this term as n approaches infinity, this just equals to 0. So you're left with 0 minus 1, which is negative 1 on the top. And on the bottom, you're left with a half minus 1, which is, well, simply negative a half. And this is equal to 1 divided by a half, because the negatives cancel, which is equal to 2. There we are. So therefore, we're just integrating x to the power of 2. And the integral of x to the power of 2 is equal to, this is the easiest it's going to get today, x to the power of 3 divided by 3 plus c. There you go. Alright, next for our fourth integral, the integral of cosecant x plus cotangent x dx. How do we do this? First, just to make our life a little bit easier, I'm going to split the integral into two. So this is equal to the integral of cosecant x dx plus the integral of cotangent x dx. And now we can treat these two integrals as independent. So, what should we do? The integral of cosecant x dx is equal to, how do we work this out? I'll show you the trick. This trick works for if you have secant as well. I'll show you what we do. So we multiply the top and the bottom by cosecant x plus cotangent x, right? In other words, I'm just multiplying by 1, or I'm just changing the form of the integrand. I'm doing nothing special. So this is just equal to the integral of cosecant squared of x plus cosecant x cotangent x dx all over cosecant x plus cotangent x. I'll just write cotangent x first. Why not? Doesn't make a difference. Alright, now if you're doing A-level maths, you will know that here we can apply something called the reverse chain rule. But if you're not, then I guess we should just take a substitution. Let's let u equal to the denominator, like this. And so du is equal to negative cosecant squared of x minus cosecant x cotangent x, all multiplied by dx. And so I can rewrite the right hand side as, like, you know, put the negative on the outside. Cosecant squared x plus cosecant x cotangent x dx. Right? That's all I'm doing. And this means that negative du is equal to cosecant squared x plus cosecant cotangent, of course, dx. And what do you notice? This bit over here in our integrand is actually equal to du. Negative du, sorry. So this integral, if we take it to being in terms of u, we just get, I'll put the negative on the outside of the integral, and we have 1 on the numerator. On the denominator we have u and du. This is clearly equal to negative ln of absolute value of u, which is equal to negative ln of absolute value of whatever u was that we picked. Cosecant plus cotangent. Alright, that's our first part of the integral. What's the next part of the integral? I'll just separate it like this. Next part of the integral is to integrate cotangent. So I'll do it here. Integral of cotangent x is dx is equal to, well, the definition of cotangent is simply cosine over sine. And now let's take a quick substitution. U equals to sine of x. Of course you could guess and check as well, but I'll do a substitution just to be fully sure, and I'll differentiate both sides, and this is just equal to du. So you have 1 over u du, which is ln of u, which is ln of sine of x. Now, I do realize I've made a slight mistake, and that is reusing u again for the same question. Perhaps I should have used v or w or something, but it shouldn't matter too much. Let's just let it slide. So then, therefore, this integral is equal to this bit here plus this bit, which is, I'll write the sine first, ln of sine x first, minus ln of cosecant plus cotangent x. And if we, this is the answer, but let's just combine the logs to make it look nicer. Ln of sine over cosecant plus cotangent x plus c. Now, maybe we could simplify this further by writing cosecant and cotangent in terms of sine and cosine, but I don't really think there's any point in that. Well, cosecant is 1 over sine, cotangent is cosine over sine. If I multiply everything by sine, I'd get sine squared on the... In fact, I'll just do that quickly. So ln of sine x on the top. On the bottom, we have 1 over sine. On the plus cosine over sine. And if you multiply everything by sine, you get sine squared on the top and 1 plus cosine on the bottom. But, well, we haven't really changed anything. They're the same thing. I'm just doing this because perhaps in a textbook they might give you this answer. Who knows? So there we go. Now we have integral number 5. What is this? I'm a little bit scared. What? How are we meant to do this? What is this limit? Well, actually, it turns out that this is equal to e, this bit here. And I'm going to prove that to you right now. Let's do it in blue. So the limit as n goes to infinity of 1 plus 1 over n all to the power of n equals to, let's call it L. The purpose of this is so that we can do some manipulation later. So let's apply natural logs to both sides. So ln of the limit is equal to the limit of the log. So I'll put the limit on the outside, and then I'll put the log on the inside of the limit. Okay, now this is what we have. The idea is, because this is log properties, we can put this n to the front. I'll just do that right in one go, like this. There we are. So this can be rewritten as the limit as n goes to infinity of the same log over n to the power of -1. I'll write it as 1 over n. The purpose of this is so that we can use something that I introduced to you in the previous video called L'Hopital's rule. I'll just call it LHR. The idea is, if you have the limit as some variable approaches some constant of two functions divided by each other, you get the same limit as the same variable approaches the same constant, of the only difference being those two functions' derivatives, like this. So all we need to do is find the derivative of the top and of the bottom and divide them by each other. I'll just rub this out, we don't need this anymore. So the derivative of the bottom, 1 over n, let's work that out quickly. So 1 over n d over, well, this is too small, I need to write bigger. D over dn 1 over n is just equal to negative 1 over n squared. Cool, we got that. How about when it comes to the log? So d over dn ln of 1 plus 1 over n is equal to, well, the bottom is what the argument of the log was, and on the top of our fraction we'll have the derivative of the argument. The derivative of 1 is 0, the derivative of 1 over n has already been worked out, negative 1 over n squared. So therefore this ln of L can be rewritten as the limit as n goes to infinity of the derivative of the top, which we worked out to be negative 1 over n squared all over 1 plus 1 over n, divided by the derivative of the bottom, which is negative 1 over n squared. And what you notice is this thingy cancels out with that thingy, and you're left with simply ln of L is equal to limit n to infinity of 1 over 1 plus 1 over n, which now you can plug in infinity into our limit, and you get 1 over 1 plus 0, which is 1 over 1, which is 1. Why did we use L'Hopital's rule in the first place? Well, the idea behind it is, if we were to immediately sub in infinity into our n's, we would get something in the indeterminate form. For example, here, sub in infinity into there, you get 1 plus 1 over infinity, which is 1, plus 0, which is 1. And then infinity into the top, and you get infinity. So you get 1 to the power of infinity. And you may say, is that 1? Well, actually, that is indeterminate. We don't know what it is. Because, well, it's not quite 1, right? That's why it's indeterminate. If you put infinity into this n and that n, you end up with a situation where you get like infinity divided by 0, pretty much, whatever it is. 0 divided by 0, sorry. And that's illegal, that's indeterminate. So we had to use L'Hopital's rule, and we got the limit ends up being 1, right? I mean, ln of the limit, sorry. So now we just apply e to both sides. So L is equal to e to the power of 1, which is e. There you go. I've proven to you that the limit is e. Let's go back to the integral. So this integral is simply equal to e to the x sine x dx integrated with respect to x. And for this, let's use the di setup once again. So what should we do? Let's put d here and I there. So let me think. Actually, I'll put them on the side like this. di. So let's differentiate sine and integrate e. There is no difference really, because in terms of what trig, what function you choose to differentiate and what you choose to integrate, but I'm just going to choose to differentiate the trigs because it's a little bit easier. So that's what we get, and I'm going to stop there because we get a loop. So let's multiply these, and then the product of a row is the integral. So this integral is actually equal to e to the x sine of x minus e to the x cosine of x. And of course, I'll just move this upwards, like there. There we are. And then finally, minus the integral of e to the x sine x. And the point is, this term over here is the same as that term over there, so we can combine them onto the same side. So we get 2 lots of e to the power of x sine x dx is equal to e to the x sine x minus e to the x cosine of x. And finally divide both sides by 2. The integral we were trying to find is equal to half of e to the x sine x minus half of e to the x cosine of x plus c, and we are done. That's a lovely, lovely integral, and we had to do a limit to infinity somehow. I'll just highlight everything. There we are. Now we have question number 6. Integral of arcsine of root x dx. This is similar to question 1 but slightly different. The differences are, firstly, the argument of the arcsine has been replaced from x to being root x, and secondly, there is no squared on the arcsine. So you all know I hate working with surds. Let us remove that surd by doing a little substitution. U equals root x, square both sides, u squared equals x, apply the implicit differentiation to both sides, and you get 2u du equals to dx. And finally, well, not finally, nextly, is that even a word? Bring this integral into being in terms of u. So you get arcsine of u multiplied by 2u du. So I'll put the 2u first, and I'll put the arcsine of u du. Now I think I should take another substitution. Let arcsine of u equal to t, so that u is equal to sine of t. All I did was apply sine to both sides. Differentiate both sides implicitly. You get du equals to cosine of t dt. And finally, you need to bring all of these u terms into t terms. So u is sine of t. Arcsine of u is t. I'll put the t first before the sine. So 2t sine of t, and then dt is cosine of t. Sorry, du is cosine of t dt. Now, if I were to put the t first and then put the 2 after it, there we are. Now we get another opportunity to apply a trig identity. This is actually equal to sine of 2t. So this integral is equal to the integral of t times sine of 2t dt. And if we do if we do integration by parts, let's do di again. Let's differentiate t so that we get simpler and simpler as we go, and integrate sine of 2t. Differentiate t, you get 1. Differentiate 1, you get 0. Integrate sine of 2t, you get negative a half of cosine of 2t. Integrate that, you get negative a quarter of sine of 2t. Okay, cool. Now let us multiply the diagonals. The product of a row is an integral, but given that we have a 0 here, that cancels out. So we're left with this integral is equal to negative a half t cosine of 2t. I don't think I can fit it in. Plus 1 over 4 sine of 2t. I'll write it like this. Negative a half t cosine 2t plus a quarter sine of 2t. The reason why there's a plus there is because the plus and the minus cancel out. So that's what we have. Let's just replace the cosine of 2t in terms of t and sine of 2t also in terms of t. So we get negative a half t multiplied by whatever cosine of 2t is. Let's use the double angle formula. It's actually equal to cosine squared of t minus sine squared of t. So let's write it like that. There you are. And then plus a quarter multiplied by sine of 2t. Well, sine of 2t is equal to 2 sine of t cosine of t. The 2 can reduce the quarter into a half, and then we have sine of t cosine of t. I nearly wrote cotan. So the final step is to replace our t's with u's and then our u's with x's. So given that u is equal to sine of t. We don't know what cosine of t is, so let's draw a right angled triangle to accompany this, and the opposite will be u, the hypotenuse will be 1, the adjacent will be 1 minus u squared all squared. All square rooted, sorry. So this integral in terms of u will equal negative 1 over 2 t, which is arcsine of u, multiplied by cosine squared, which is root 1 minus u squared, all squared, where the roots cancel out. So we have 1 minus u squared. And then minus sine squared of t. Sine squared is just u squared, right? Of t, of course. So minus u squared. Plus a half sine of t cosine of t. Sine of t is equal to u, and cosine of t equals to root 1 minus u squared, if you look at the triangle. Right. And if we were to simplify what's in this bracket here, this is just equal to 1 minus 2u squared. And finally, the last step is to take everything from u's to x's. So minus a half, let's see, u is equal to root x and u squared is equal to x. So arcsine of u becomes arcsine of root x. And then multiplied by 1 minus 2u squared, which is 1 minus 2x, because x is u squared. And then plus a half u, which is root x, multiplied by root 1 minus u squared, which is x, plus c, and we are finished for that one. Let's see what's our next integral. Number 7. We still have 4 more to go then. The integral of 2x over x to the power 4 plus 1. Now, maybe you could do some awkward looking partial fractions for this, but I'm not convinced. I don't think that would work. Probably doesn't. Instead, I have another way to do it. Let's rewrite the denominator like this. So the x to the power 4 can be written as x squared all squared plus 1. And this calls for a substitution. Let u equal to x squared. I'll write the substitution here. So du is equal to 2x dx. I know I'm forgetting the dx. I'll just quickly write it here. And what do you know? This bit here is equal to du, and this bit here is equal to u. Of course, we have u squared plus 1. So our integral can be put in terms of u. We have the integral of 1 over u squared plus 1 du, which, spoiler alert, actually equals arctan of u. How do I prove that my claims are correct? Well, let's do another substitution. Let u equal to tan of theta. Yes, we're using theta for the first time in this video. Round of applause for me, please. Differentiate both sides implicitly. You get du equals secant squared theta d theta. And if we put this integral in terms of theta, we get 1 over u squared, which is tan squared of theta, plus 1, multiplied by du, which is secant squared of theta d theta. And this denominator can actually be rewritten as secant squared of theta, and it cancels out with that secant squared, so we just end up integrating regular old theta, regular old 1, sorry, not even theta. So we're just differentiating d theta, sorry, integrating, and you get theta, which is equal to arc tan or inverse tan of u. Finally, bring that there and replace the u with the x. U is equal to x squared, so the answer to this is arctan of x squared plus c. Perfect, and we are good to go. Next integral. We have number 8 here. Who put a partial derivative in this? What are you doing, man? Okay, let's just work out this partial derivative first, then we can integrate it with respect to x. So the idea of a partial derivative is you assume that the a variable is independent from the x variable. So, in other words, if you do a partial derivative in respect to a will be treated as the variable, x will be treated as a constant. So, in other words, this integral, sorry, not this integral, this partial derivative can be rewritten as 1 over cosine of x, because that's just a constant, multiplied by the partial derivative with respect to a of a sine of x plus 1. And if you do a derivative of 1 is a constant, 1 disappears when you differentiate it. Differentiate a sine of x, where sine of x is a constant. You end up simply differentiating a, and you get 1. Multiply that by sine of x, you get sine of x. So this partial derivative simply equals sine over cosine. Finally, let's put that into our integral, sine over cosine. And you can guess and check. I'll just do a substitution. Let u equal to cosine, so du equals to negative sine x dx. And you know what? I'll just put a negative there and a negative there. Doesn't change the integral at all. I'm just multiplying by negative 1 twice, so multiplying by positive 1, which is keeping the same thing. So if you take this in terms of u, well, what do you know? This thing equals to du, and that thing is equal to u. So we have the negative integral of 1 over u du, which is negative ln of absolute value of u, which is negative ln of cosine of x. And that is completely correct, plus c. But you notice some textbooks will write it as ln of secant x plus c. And they're both correct answers, don't get me wrong. But the way you got the second answer is by putting this negative, it's a negative 1 technically, into the log as an exponent of the argument. So you get ln of cosine of x all to the power of minus 1. And the reciprocal of cosine, not to be confused with the inverse of cosine. Reciprocal of cosine is 1 over cosine, which is secant. Okay, question 9. The integral of k sine of x all over a plus b cosine of x. That's a little bit awkward because these constants are weird. Let's just take k on the to the outside of the integral. So this integral just becomes k lots of sine x over a plus b cosine of x with respect to x. And let's take another substitution. You know, most of these integrals we're doing today are involving substitutions. It's quite fun, isn't it? So let's let u equal to the denominator and differentiate both sides implicitly. So we get negative b sine of x dx on the right hand side. Divide both sides by negative b sine of x, and you get all this. Now, next we must write this integral in terms of u. So we get k lots of the integral of sine of x over the denominator. We said the denominator was going to be u, and dx is replaced by negative du over b sine of x, and the signs, they cancel. We can put the negative in front of the integral, and we can put the 1 over b also in front. So this is equal to the integral of negative k over b multiplied by the integral of 1 over u du, which is just simply negative k over b ln of u. And finally, replace u with x, and you get negative k over b ln of u is a plus b cosine of x. So instead of u, we can just write this plus our constant of integration c, and that's our answer. Now, the question is, what would happen if we had like some invalid version of this? Well, I don't think you can get one unless you had like b is equal to 0. Then it would be very awkward. You'll just be integrating a constant, really. Well, sine. But alright, next. Oh, this is our final integral, and that's it. After this, our video must be done. Alright. So, the integral from 0 to 1, this is our first and final definite integral for the day. And the integrand is x minus 1 all over ln x dx. So, how do we deal with this? Because our usual techniques don't work. You can't take a U substitution or trig substitution. You can't do integration by parts. You would just end up with some awkward stuff which never works. You can't do anything really. No trig ideas here. No other ideas. So this calls for Feynman's trick. But before we do that, let's label this integral as I, so that we can have convenience. We don't need to write this integral 50 million times. So now let's do something called parameterization. F is our function of a new variable. What should we call our new variable? I'm going to call it t. Why not? I'll just call it t. F of t is equal to the integral from 0 to 1 of our integram. Now, what I'm going to do is copy this integram into there, but change it up a little to include t. So let's do this. X minus 1 over ln x dx. Let's put a t as a power of x like that. What's the reasoning behind this? Well, the idea is if you differentiate both sides with respect to t, you'll end up with a partial derivative on the right hand side. Or in other words, you're going to be differentiating under the integral sign. So you're going to end up differentiating x to the power of t partially with respect to t. That allows you to produce x to the power of t times ln x, which cancels out with the denominator. I'll show you after we quickly write that all of this shows that I is equal to f of 1. Basically sub in t equals 1 into there and you get the answer. And also, if you sub in t is equal to 0, you get x to the power of 0, which is 1, minus 1, which is 0, and your entire integral collapses to 0. So this is convenient for later when we end up having to solve some differential equations. Let's first differentiate both sides with respect to t. So I'll write d over dt on both sides like this. So on the left hand side you simply have f prime of t, and on the right hand side you have a partial derivative with respect to t like this. X to the power of t like that, minus 1 all over log of x. And then if we were to put brackets like this, just to make things slightly easier to read, like that. Alright, so this partial derivative actually works out to be x to the power of t. I'll show you why. Let's just write all the steps out to make it easy for you all to see. So if you differentiate negative 1 with respect to t, negative 1 just becomes, it's a constant, so it differentiates to 0. I'll cross it out so we don't need to worry about it. If you differentiate x to the power of t, of course partially with respect to t, where you treat x as a constant and t as a variable, this would end up it would end up becoming x to the power of t times ln of the base. So let's say you wanted to differentiate 2 to the power of t. That would just become 2 to the t ln 2. This is the same thing as that, except instead of a 2 we have an x. So we end up with x to the power of t ln x like this. I'll write it in white. X to the power of t ln x, and on the denominator we have ln x. The reason we have that staying the same is because it's just a constant multiple. The logs cancel and we end up with a very simple integral, just x to the power of t. And now we treat t as a constant and x as a variable, and just do a normal integral really. You get x to the power of t plus 1 over t plus 1, and remember we have our integration limits at 0 and 1. If you sub in 0 into x, well, you just get 0. If you sub in 1 into x, you get 1 as our numerator over t plus 1. So that's what our f prime of t is. The next step is to work out what f of t is in terms of just t and nothing else. No x's, just t. So the solution to find that out is to just integrate both sides with respect to t. So you end up with this. The integral of f prime of t dt is equal to the integral of 1 over t plus 1 dt. And the left hand side, 1 second, let me just put this line longer. The left hand side, the integral cancels out with the prime and you're left with just f of t. I'll put the t in blue. And on the right hand side, you just end up with an indefinite integral, but quite a simple one. You just end up with ln of t plus 1 with the modulus, don't forget that, plus c, which is our constant of integration. Now, the next step is to work out what this c is equal to, because if we can't work that out, we can't work out our answer. Our answer will just be in terms of c, and that's quite awkward. So remember, if we scroll up a little bit, where is it? Here, we said that f of 0 is equal to 0, right over here, right? So if I were to sub in t equals 0 into this, I'll just get f of 0 is equal to ln of 0 plus 1, which is ln of 1, plus c, which is equal to 0, right? And what is ln of 1 precisely equal to? This is equal to 0, so we can just ignore it, cross it out, and so c is also equal to 0. So our f of t can be redefined as ln of absolute value of t plus 1, and well, our plus c is just plus 0, which we can just ignore. So the very, very, very final step is that we need to acknowledge the fact that I is equal to f of 1. Okay, I equals f of 1, because to get from this integrand to that integrand, why am I drawing a curly arrow as if it's a mechanism from organic chemistry? Well, if you replace t with 1, you end up with the original integral, which we called capital I. So let us replace t with 1 in our integral, in our f of t. So f of 1 is equal to ln of absolute value of t plus 1, which is 1 plus 1, which is 2. And that's our answer. I'll just write it in one nice line over here. The integral from 0 to 1 of x minus 1 over ln x dx is equal to what? ln of 2. That's our answer. I'll highlight it again. I hope you enjoyed this video. I hope it was useful. Perhaps you could use it as a revision tool. Perhaps you could use it to, share it with your friends, learn some new stuff. And if you already found all these integrals easy, at least it serves as a reminder. So please, once again, like, subscribe, share, comment, give me feedback. If I made any mistakes in this video, call it out. And if ever you find an easier way to do any of these, please write it in the comments below. If you're confused about anything, ask me. Please don't say you're confused about the definition of arcsine. I will be very interested to know why that is. Alright, so thank you for watching this. I hope you enjoyed, and it's 11 o'clock, so I guess good night or something.